Now let's look at one more example using motion graphs. The following question presents a velocity time graph, and it represents, as stated in the question, a ball rolling on a ramp. So the first thing that I strongly recommend you do when you stumble across a problem like this is to ask yourself, okay, what does this graph actually represent? What's it actually showing me? So we know it's a ball rolling up a ramp. And I always recommend drawing some kind of little diagram to represent what's happening. So we've got a ball and a ramp. And let's try to see what this graph is telling us is happening. So you see where we start, our velocity is 1.2 meters per second at time 0 seconds. So that means we have a ball that is rolling at 1.2 meters per second. At this point here, the velocity starts to decrease. And that means our ball is going up the ramp and slowing down until at 6 seconds you see the velocity reaches 0. And that's when it's at the top of the ramp. And then as time continues to pass, what happens? Well, the velocity becomes negative. And I will add a note here that positive velocity is towards the right, negative velocity is to the left. So after our velocity reaches 0 at 6 seconds, ball's at the top of the ramp, then what happens? Well, we start moving with a negative velocity, and our ball starts rolling down the hill slowly, and then it speeds up as it goes. Once it reaches the bottom, we then have a constant speed of negative 0.2 meters per second. So it stops accelerating, but it just has a constant speed. And then our observations stop after 12 seconds. We don't know what happens to the ball after that, and we don't care. So now that we have an idea of, okay, we know what generally what's happening, we can start answering some questions. So at what time is the ball at the top of the ramp? Now, how do we know when the ball's at the top of the ramp? Well, we know because the ball reaches a speed of 0 meters per second when it's at the top, just before it starts coming back down again, right? So when we look at our graph, where is our velocity? 0 meters per second. Well, it's at 6 seconds. So first question is simple as that. When velocity equals 0 meters per second at time equals 6.0 seconds. Put a box around our answer to make it clear, and we'll move on to part B. How fast was the ball traveling along the floor? Okay, so we're going to use our graph here. At what point on this graph is the ball traveling on the floor? Well, it's at the beginning and the end. So the answer here is we're going to look at, especially the positive answer, 1.2 meters per second. And technically, if you wrote negative 1.2 meters per second, that would also be correct, because you'd be talking about this part here. And that is also when the ball's on the floor. But for simplicity's sake, we call it 1.2 meters per second. What was the ball's acceleration while on the ramp? So remember, when we're on the ramp, we're looking at this section here, this section here. We should know that for the acceleration, we have a formula. That is the change in velocity over change in time, or velocity final minus velocity initial over t final minus t initial. Now the question is, what points are we going to use as our final and our initial? Well, looking at our graph, we know from earlier that the ramp section begins here and ends here. So where would be the best places to calculate the acceleration from? The answer is we can put our points anywhere along this line. So what we're going to do is pick points that make it the easiest for us. And that's generally looking at the time. We want a nice clean number. Here, 1.5 is clean enough. And here, a 0 is always a nice point to use because 0 is probably the easiest number to work with. So here we have our 2 points, and we're just going to plug them into the formula. So this is our second point, and this is our first point. So, let me change these to F for final and I for initial, because that is the subscripts that we're using in our formula here. So 0 minus 1.2 meters per second over 6 seconds minus 1.5 seconds. We'll find that gives us or equal to 0.266 repeating. We want our final answer with a couple decimals. Just like that. It's important to also note the units here, and acceleration is meters per second squared. So moving on to part D, what was the total displacement? Now, how do we calculate the displacement? The displacement on a velocity time graph is the area underneath these curves. And by underneath, what we actually mean is between the curve itself and the x-axis. So here we're looking at this area that is under the curve, and here we're looking at this area. So the displacement is the area under the curve. This is important to know and to memorize, specifically in a velocity time graph. If you're given a position time graph, this won't work. The displacement is the area under the curve in a velocity time graph. So the best way to find the area, as long as we have shapes that are easy to work with, we want to split up our area into simple shapes that we know how to find the area of. So these are like rectangles and triangles in this case. So we've got 4 shapes here that we're going to be calculating the area of. And you will see these areas are going to come in handy for a lot of questions. So now let's calculate the area for all these sections. A1. And what we need to do is look at the side lengths and the dimensions of each of these areas. So we know the height of A1, 1.2 meters per second. And what's the base? 1.5 seconds. So the area we know is base times height. And paying attention to our units still, we have 1.5 seconds times 1.2 meters per second. Our seconds cancel out, and our answer will be in the units meters. And that makes sense because we're trying to calculate displacement. Now moving on to our second area. What are the lengths here? So our height, 1.2 meters per second. And then our base, got to do some math here, 6 seconds minus 1.5 seconds equals 4.5 seconds. So our base of the triangle is 4.5 seconds. And how do we find the area of a triangle? 1/2 base times height. So our second area is 2.7 meters. Again, with the units seconds multiplied by meters per second, our seconds cancel out, and we're just left with meters in our units, and that is exactly what we're looking for. Now let's do A3. It's the same triangle, upside down. There will be an important step for us to catch here. So this mark here is halfway between 10 and 11, so it's 10.5 seconds. 10.5 seconds minus 6 seconds is equal to 4.5 seconds for our base. And then what is the height of this triangle? Well, it's in line with the negative 1.2 meters per second. So our height is minus 1.2 meters per second. And that minus sign is important here. The area for the triangle is the same as the last. I hope you know how to calculate the area of triangles. And what you'll see on this one, sure that should be a 3. What you see on this one is that we actually get a negative area. So negative displacement from A3. And that's, you might be a little confused at the moment, but if you bear with me here, it'll make sense once we start doing some math with that. And then same thing with area 4. This is just the same as the other ones. This should be getting easy by now. Just base times height. What is our base? Well, again, 12, sorry, I should slow down, not go a little too fast here. 12 minus 10.5 seconds equals 1.5 seconds. That is our base of our triangle, or our rectangle, sorry. And then the height, again, the negative 1.2 meters per second. So our fourth and final area here is negative 1.8 meters. All right, that was a little bit tedious, but for calculating the displacement, that is the simplest way to do it. Split up our curve into shapes that we can find the areas of, so rectangles and triangles. Calculate those areas individually, and then when we're calculating the actual displacement, we will be adding up all those areas. So the displacement is the sum of all the areas. So A1 plus A2 plus A3 plus A4. So A1, if we remember, 1.8 meters. A2, 2.7 meters. A3 was 2.7 meters minus, and then A4 was minus 1.8 meters. Now, what do you notice here? Well, our 1.8s cancel out, and our 2.7s cancel out. So our final answer for the displacement is 0 meters. It wasn't that anticlimactic. All that work just to calculate 0 meters. But does that make sense? Well, let's think about it. Going back to our ball down here. At time 0, we have our ball in its position at the base here. As time passes, our ball rolls up the ramp, slows down, and then speeds up down the ramp. And where does it land? Well, it lands in the exact same place that it started. So our total displacement is 0 meters. Now looking at part E, we have a slightly different question. That is, what is the total distance traveled? Now, the distance is slightly different from the displacement. We note it with a D, but without the vector symbol above it, because distance is not a vector. And what it is, it's the areas. Here, I'll write it like this. It's the same areas, but the only difference is that we don't care about direction here. We only care about distance, and there's no direction associated. So whether it's positive or negative makes no difference to us. We just want to add up the absolute values. So that's what these lines indicate, is absolute values. So now when we're doing our math, we will see 1.8 meters. Sorry, wrong color there. 1.8 meters plus 2.7 meters. And then here's where the difference will come in. The absolute value of negative 2.7 meters is positive 2.7 meters. So we're adding it. And same with the fourth area, we're adding 1.8 meters. So this becomes a sum of these areas. So with distance, we don't care about whether it's forward or backwards. All we care about is that it was a distance that was traveled. So when we're adding them up, we will get a final answer, D equals 9 meters. So that means in the time that the ball was rolling, in the time that the ball was rolling, from the time we start the stopwatch, goes up the ramp and then back down. In that time, the ball traveled a total distance of 9 meters. And the last question, part F, how long was the ramp? Now, some of you might be able to already know how long the ramp is just by looking at what we've done so far. But the strategy here is to look at our graph, think, okay, what part of our graph here represents the ball on the ramp? Well, it's this diagonal here, right? So when we want to know how long the ramp is, we're asking for what is this distance? How long is that ramp? So if we can find out from the time the ball hits the ramp until the time that the ball's velocity reaches 0 and it's at the top of the ramp, how much distance was traveled? And the answer to that is looking at some of our areas. If we look at the area A2, what does that show us? Well, that shows us the distance traveled from the time the ball reaches the bottom of the ramp until the time the ball reaches the top of the ramp. So A2 is actually the length of the ramp. All right, now let's just make sure that we understand everything that's happened so far. So looking at this, I always like to look at these questions visually. Using these little diagrams, you can always draw them on your test. Just beside the question, draw a little sketch of, okay, what's actually happening. So what we see here, when time equals 0, our ball sits and it is rolling with a constant velocity on the ground until time equals 1.5 seconds, at which point it begins to roll up the hill. And once it reaches the top of the hill, the time equals 6.0 seconds. And during this period, our velocity is plus 1.2 meters per second. And I can draw a little legend for us here. Okay, so once our ball reaches the top of the hill, top of the ramp, then what happens? It starts rolling back down. Comes down the hill. And then once it reaches the ground again, it rolls across the ground with a new velocity of negative 1.2 meters per second. And that occurs from time equals 6 seconds. And it reaches the bottom of the ramp at this point here. Time equals 10.5 seconds. And then by the end, when we stop the stopwatch, is that time equals 12 seconds. Now let's try to understand here what's happening on the ramp. So on the ramp, we have an acceleration that occurs. An acceleration. Now you might be thinking, well, to me it looks like a deceleration because our speed is actually slowing down. And that is correct, because we do have a negative acceleration. It is, you could also call it a deceleration or a negative acceleration. They're the same thing. You would be correct in saying that our ball is decelerating or accelerating to the left 0.27 meters per second squared. So on this region here, our speed, or velocity rather, changes because acceleration occurs. And then when we're on the ground here, the velocity is constant because there's no acceleration.